Hi everyone, in this video we're going to go through a number of transformations of graphs. So in the last video we did basic functions and their graphs, and now we're going to start transforming some of them. So graph the parent function f of x equals x squared. So the parent function is the basic function. And so we graphed this previously, so I'm going to just do it really quick. This is a parabola, it's a quadratic function. So 0, 0 is a point. 1, 1 is a point, so is negative 1, 1. And then 2, 4 is a point. Negative 2, 4 is a point. And then I'll do extra one from that we didn't do in the last video. 3, 9 would be a point. And then negative 3, 9 would also be a point. And so here is our parabola. Okay. Our standard parabola or basic function or parent function. Alright, so that's f of x equals x squared. What's the domain of this function? Well, we've talked about that. Any x number can get plugged in and you'll get a y value that comes out. So negative infinity to infinity. What's the range? That's the y values. This graph, the lowest point is 0 and then the rest all are going up all the way up to infinity. So from 0 to infinity, and then we have a bracket because we can equal the point at 0, and then parenthesis because we can't ever equal the infinity. Predict what you think the graph of y equals negative x squared will look like. Describe any similarities or differences you think this graph will have from the parent graph above. Okay, so I want you to figure that out, see if you can predict what it'll look like, and then we'll go ahead and graph what it'll look like in just a moment. Okay, so on the next page we're actually going to graph that function, and depending on what you thought, let's see if what you thought will be what comes out. If we start plotting some points, so I'm just going to make a quick side table for x and y values. If we start plotting just a few points here, we'll get this graph pretty quickly. So y or f of x is our output. I'm going to pick negative 2, negative 1, 0, 1, and 2. And so this time there's a negative in the front. And whenever you substitute into a function, you always put parentheses around where x was. So this is negative, and then parenthesis, negative 2 squared. So we're squaring this negative 2, and then there's still this negative out front. So this is going to be 4 with a negative, so this is negative 4. So I'm going to start plotting that. I don't quite have my grid lines on this one, but this is negative 2, and then down here is negative 4. Okay, negative 1, when I plug that in, I still have my minus out front from before, and then negative 1 quantity squared, that becomes positive 1, but then the negative is still out front, so negative 1. So negative 1, comma, negative 1. 0, well 0 squared is still 0, and then with a negative it doesn't change anything, it's still 0. 1, if I plug in 1, I get negative and then 1 squared, and so that's positive 1 when you square it, but then there's still a negative out front, so that's negative 1. So 1 comma negative 1, and then when I plug in 2 I have negative, and then 2 squared is 4 with the minus is negative 4, and so that's 2 comma negative 4, and then this is a parabola, and this time it is going downward. So is that what you predicted? If so, then you were right. The minus sign in the front actually flipped our graph down. So was your prediction correct? Describe the transformation from the parent graph, and you can say something like the graph flips vertically, or reflects. That's another word that we use a lot. So flips vertically, that's the original graph was up here. You could think of it as flipping down. Flips vertically, or you could say reflects. And we would say where it reflects, it reflected about the x-axis. Reflects about, or like over, the x-axis. Okay, so a negative in the front of the function actually flips it or reflects it. The domain of this new function, it's still all real numbers. You can plug in anything you want for x and you will get a y value out. The range this time though, notice the y values. This graph, the highest point is now 0. Last time the lowest point was 0. So the range, the highest number we're ever going to get out is 0. And then this graph goes all the way down to negative infinity. But you always start with the lower number. So you say negative infinity until 0. Because you start with the lowest value and then you go all the way up to the biggest value. So your graph goes from negative infinity up toward 0. 0 being the highest point on the graph, and bracket because there is a point that we can equal. Alright, so that's one transformation. If we put a negative sign in front of our function, it flipped it vertically. Next, predict what you think the graph of y equals 3x squared will look like. Describe any similarities or differences you think this graph will have from its parent function, the original one we looked at, the original one we graphed x squared. And then predict what you think the graph of 1/3 x squared will look like, and describe any similarities or differences. Okay, so let's go ahead and graph these two functions, y equals 3x squared and y equals 1/3 x squared. So let's just make a quick table for each of these and plot some points. So on the left, I'm going to use the y equals 3x squared, and then on the right, I'll make a different table. I will have y equals 1/3 x squared. So we are going to have two separate graphs in our same grid here, our same coordinate plane, but we're just plotting them one at a time. And so let's pick our same x values we've been picking. It'll work out just fine on this one. So this time I have x squared but times 3. Remember order of operations, you're going to do exponents first. So this is 3 times negative 2 squared. And so exponents first, this becomes 4. So 4 times 3, this is 12. Okay, 3 times negative 1 squared, this becomes positive 1 times 3, so 3. 3 times 0 squared, well that's just 0. And then 3 times 1 squared, that's 1 times 3, which is 3. And then 3 times 2 squared, exponents first, so that's 4 times 3, which is 12. Okay, let's plot these points. So negative 2, comma 12. 12 is a little bit up off of this graph here that we have, this grid, but we can still throw it in here, plot that up there. Negative 1 goes up to 3, and then 0, 0, 1, comma 3, and then 2, comma way up here at 12. Okay, and it's still x squared, so it is still a parabola shape. So let's try to draw this. And there it is. This is 3 times x squared. Okay, so let me just show you really quick. Let me bring back the original and compare these two. So if you compare these two, this one is looking more narrow. So it's looking like I kind of like grabbed this graph and stretched it vertically. This one's thinner or more narrow, stretching vertically. And that's going to happen anytime you multiply by a value like this, bigger than 1. And I'll summarize that in just a moment. Let's go ahead and plot the next one. Okay, just to not confuse us, I'm going to switch colors. I'm just going to go to red so that we have two different graphs we're looking at. So in this one, I'm going to pick the same x values one more time. Okay, so this is 1/3 times negative 2 squared. Exponents first, this is 4 times 1/3. So this is 4/3. 4/3 is the same as 1 1/3. That might be easier to graph if I write it like that, 1 1/3. Then 1/3 times negative 1 squared. So this becomes positive 1. And then times 1/3 is just 1/3. 1/3 times 0 squared is just 0. 1/3 times 1 squared is 1/3. And then 1/3 times 2 squared, that's 4 times 1/3, that's 4/3 again, and that's the same as 1 1/3. Okay, let's plot these points. -2, and we're going to go up just 1 and a tiny bit more. So -2 and go up, here's 1, so a little bit more, like right there. -1, I'm just going to go up 1/3, not very much, that's like 0.3, like right there. 0, 0, and then 1, and then up 1/3, and then 2, and up 1 and 1/3, so just right there. Okay, and this is still a parabola shape, but this one's a little funnier looking. This one is wider. Okay, so that's our second graph there. All right, and let's compare it to the original again. This one does look wider than the original. Here's the original. This one's much wider. And so it's like I took this graph and I stretched it horizontally, or like compressed it. It got wider. All right, so was your prediction correct? That's for you to answer. So what did you determine what this was going to look like before we actually graphed it? Now describe the transformation. In general, notice we're replacing the numbers 3 and 1/3 with a from the parent graph. So the transformation means that we've transformed that original x squared graph, we've transformed this graph to look different. It's still, all our graphs are based on this, but they just look different. We've transformed it, it looks different. And so we have two situations here that we'll mention. On this one, we have two different outcomes. One if a is more than 1, and the other is if a is less than 1. Okay, so when a was bigger than 1, that was this example where we had 3 times x squared. So this one we would say that our graph is stretching. So stretched our graph vertically stretching our graph, pulling it vertically to make it look more narrow. And this is by a factor of a. So stretched vertically, specifically by a factor of a. If a is less than 1, so if we times our function by something less than 1, a fractional amount, then it's actually making it look wider. The graph is looking wider. So you can say something like stretched horizontally, or you can also call this compressed vertically. So I'm going to put this in parentheses. Stretched horizontally, which you can also call that compressed vertically. So instead of it stretching up, it's actually getting compressed down. So compressed vertically. Okay, and this is stretched horizontally by a factor of a, or compressed vertically by a factor of a when a is less than 1. Okay, what's the domain of the first function? Well, for all quadratic functions, it's always going to be all real numbers. So same thing for the second function. You can plug any number in for x and you will always get a real number out for these quadratic functions. The range is different though. The range can vary. Depends on your graph. So the range of y equals 3x squared, well, it's not very different than our first one actually. We start at 0 is as our lowest y value and it goes up to infinity. And that's actually true for the next function as well, for the red one. So for the red one, our lowest point is 0 and our highest point goes up to infinity. So then let's predict what's going to happen next. If you have your x squared parabola, but then you add 4 to it. And then what happens if you have x squared and then you subtract 4? So go ahead and make your predictions and then we'll graph those. So on this one, again, I'm going to do my tables. We have two separate functions we're graphing in the same coordinate plane here. And let's just go ahead and pick the same x values, it'll work out on this one just as well. X squared plus 4. So I'm going to pick -2 until 2. Okay, so let's plug those into x. -2 squared plus 4. So that's 4 plus 4. So this is 8. -1 squared plus 4. That's 1 plus 4. So we get 5. 0 squared plus 4 is just 4. +1 squared plus 4 is +1 plus 4, which is 5. And then 2 squared plus 4 is going to be 8 again. Let's plot those points. So -2 and then up to 8. 1, 6, 7, 8 is about right there. -1, we go up to 5. 0, we're right here at 4 for the y. 1, we're back up at 5. And then 2 up at 8. Okay, so check out this parabola. This one's a little different. This is actually our same exact shape as far as width goes. Like, it's not wider or more narrow, but it is moved. So if I compare it to the original one, it's the same size and everything, same shape. Nothing got narrower or wider or flipped. It just moved. It moved up. And so let's do the next one real quick. And if you didn't know, if your prediction wasn't correct, you can kind of make a new prediction real quick as we prepare this one based on this graph, what you think is going to happen if we subtract 4. So x squared minus 4. Let's pick our same x values. Okay, so -2 squared minus 4, that's 4 minus 4, 0. And then we have -1 squared minus 4. And then we get 1 minus 4, which is -3. 0 squared minus 4, that's going to give us -4. 1 squared minus 4, that's 1 minus 4, which is -3. And then 2 squared minus 4, 4 minus 4 is 0 again. Okay, so -2, comma 0. Okay. -1, comma -3. Okay, let's see, that's about, my tick marks are a little bit off, but it's about right there. 0, -4, 1, -3, and then 2, 0. Okay, was your prediction correct? Look at that one. It is the same shape parabola, but it has shifted down. Okay, it has moved down from the origin. Our original parabola was centered right here at 0, 0. But when we subtracted 4, it shifted down 4. When we added 4, it went up 4. So let's generalize this. Was your prediction correct? Let's describe this transformation in general. So if we add k. So if k is positive, that's going to do one thing to our graph. If k is negative, that's going to do something different. So if k is positive, if we add a positive number to our function, our original function, then it's going to actually shift our graph. So shifts the graph up. So shifts k units up. And then if k is negative, so we would add a negative number, so like it would look like minus a number, so -4. That would shift the graph down. K units down. Okay, so the transformation here is that your original graph transformed by shifting up or down. So that was the transformation here. What's the domain? Again, it's all real numbers for all quadratic functions for both of these. The range, this time is the first time the range changes. The blue one, when we added 4, the parabola moved up, and so notice the lowest y value is up here at 4. And then your graph goes up. Your y values are bigger. So it goes from 4 to infinity. And then you put a bracket because you can equal that point right there. when we subtracted 4, our parabola moved down, so our lowest y value was at -4, and then the rest of the graph goes up. So it goes from -4 all the way up to infinity, again with a bracket there. So we have quite a few transformations so far, and we're working our way through the rest of them. But so far the graphs can flip, they can transform by flipping, they can stretch or compress, and now they can shift up or down, okay? So go ahead and predict what you think would happen to a graph if you have this type of situation, x minus 4 squared. Notice the x minus 4 is in the parentheses and then squared. And then if you had x plus 4 parentheses squared. So make that prediction and then we'll graph these ones. Okay, let's see if your predictions come true. I'm going to use our table again over here. So we have, this time I'm actually going to pick different x values, and I'll explain why. So this one is x minus 4 squared. Okay, so here's why. And it's partly because I recognize what's going to happen. And so you might not know this right away, but I'll explain it. And so in the future you can use this. You want to pick a number in the middle of your table that makes this quantity squared 0, because if you think back to the original function, I didn't use a table on this one, but we did when we graphed this in the previous video. If I plug in my standard numbers that I kept plugging in, my 5 numbers I kept picking, I had 0 in the middle, and then 0 squared was 0. Okay, and then notice there was symmetry around that point. Okay, so when I plugged in 1, I would get out 1. When I plugged in -1, I would get out 1. When we plug in 2, we get 4, and -2 gives us 4. So there was symmetry around this point. And so I was strategically thinking about that, and then here's what I'm going to pick this time. I want this quantity that's squared, I want the inside to be 0. So I'm going to pick 4 in the middle of our graph here. Okay, so if I pick 4, 4 minus 4 is 0, 0 squared is 0. And then I'm going to pick numbers around 4. So I'm going to pick 5 and 6, and then smaller than 4, I'm going to pick 3 and 2. Okay, so if we plug in 5, we have 5 minus 4 squared. This is 1 squared, which is 1. And then notice what happens if I plug in 3. 3 minus 4 squared with parentheses is -1 squared, which with the parentheses gives us +1. And then 6 minus 4 squared is 2 squared, which is 4. And then 2 minus 4 squared, that's -2 squared, which is also 4. So watch when we plot these points, you'll see the symmetry. 4, 0. Let's go to 5 next. 5, 1. Let's go to 3. 3, 1. Okay, let's jump back to 6. 6, 4. So that's up there. And then last point up here, 2, 4. Okay, so here's why that was a good choice for picking 4 in the middle of our table, is because that was actually the center of the parabola. And we'll get into this in the future videos, but that's called the vertex. And so there is this parabola. Okay, so take a look at this compared to our original. Our original was centered at 0, 0. The vertex was at 0, 0. And this one here shifted to the right. So it moved over to the right. Okay, let's do the next one and then we'll summarize this transformation. So x and then y is x squared plus 4 quantity squared. All right, so think about it before I write it. What should I put in the middle of my table here? What number will make this quantity, before I square it, the quantity 0? Okay, hopefully you thought of it. -4. So -4 plus 4, when I plug that in, I'm going to get out 0 from the squared part of this. Then I want to pick numbers around -4. So around -4 is -3 and -2. And then on the other side of -4 is -5 and -6. Okay, so let's plug those in. -3 plus 4 squared is 1 squared, which is 1. -2 plus 4 squared, this is 2 squared, which is 4. Jumping over here, -5 plus 4 quantity squared, this is -1 squared, which is 1. And then -6 plus 4 squared, that's -2 squared, which is 4. Okay, so let's plot those points. I'm going to start in the middle, -4, comma 0. Then let's go -3, comma 1. -3, comma 1 is right there. Let's go ahead and go -2, comma 4. So -2, go up 4. Let's back up to here, -5, comma 1. And then -6, comma 4. Okay, and let's draw our parabola. And there it is. So this graph shifted left. So that is the transformation. So was your prediction correct? Let's go ahead and describe in general this type of transformation. So it depends on h. So if we have x minus h squared, it's going to be one shift to one direction. If we have x plus h squared, it's a different shift. So notice when we had the minus 4, we actually had to move right because we needed positive 4 to make this quantity 0. So we actually shifted right when we saw the minus sign inside here with x. So if it's x minus a number and then squared, your graph is going to shift, or the graph shifts, h units right. Oh, units to the right. And then if you had x plus a number, so back here when we needed to add, we had a number added, we had to go to -4 to make this inside quantity 0. So plus a number, we had to go left. So x plus something and then squared, your graph shifts left. And I'm trying to just make sure you see it clearly, because it might be counterintuitive. You might think negatives is left and positives right, but it's the opposite here. And the whole reason why it's opposite, why it is what it is because you have to make the quantity before you square it, you have to make that 0. So if it has a minus sign, you have to go to a positive 4 to make it 0. If it has a plus sign, we had to go to a -4 to make that 0. So that's why we went right and left respectively. All right, and then as always, the domain is all real numbers for all of these quadratic functions. The range on these ones, because they didn't shift up or down, they only shifted left or right, the lowest point is 0 on both of them, and the highest point is in going up to infinity. So they're both just the original range. Okay, so those are our transformations. We are going to do one more example where we put all of these transformations together, or a number of them together. So on this last page here, we're going to start with the prediction. Predict what you think y equals negative quantity x plus 3 squared plus 8 will look like. So you want to describe it based on what the original graph x squared looks like, and how these different things happening to the function shift or stretch or flip or whatever they do to it, how they transform it. So this one I'm actually going to talk it through with you. Feel free to pause it if you want and do your own prediction, but let's predict because we know what these things do at this point. The minus sign in front of our function that multiplies this term, that's going to do a reflection. So we could say that we think, I'll just bullet point them, that it's going to reflect or flip vertically. So the minus in the front should make this graph flip vertically. And again, you might see the word reflection for flipping. Let's go all the way to the back here real quick. The plus 8 in the back, notice it's after the squared quantity. So we did examples like this where we added something like way after the part with the x in it. So x has a quantity squared, but then plus 8 in the back. So that was when the graph was shifting vertically. So that one, because it's plus 8, we're going to shift up. So shifts up 8 units. And then the last thing we see here is that there's a plus 3 inside the quantity that's getting squared, plus 3 with the x. So x plus 3. And so if you just remember what we talked about, this one's going to shift left. But here's another way to remember it. If you have to make this inside quantity 0, you would actually have to go to -3 to make this 0. So you're going left to the negatives to make this inside part 0. So this graph is going to shift, or it shifts left. And again, we have to make this inside quantity 0, so shifts left 3 units. So shifts left 3, or you can say moves to -3 on the x-axis. Shifts left 3 units. Okay. And there's no multiplying here by something other than 1, so we don't have the stretching or compressing on this one. And then you can describe any similarities or differences. This is basically addressing it. It's going to have the same shape. That's a similarity, I would say. It's going to have the same overall shape. It's going to be a parabola as x squared, but then it will change because of these things. All right, so let's graph this. Now we have our standard parabola that we can reference. So I'm going to show you 2 ways really quick. And the whole idea of transformations, why we even care about this, is because we can graph really quickly. One reason why we care about it is we can graph really quickly. So here's our standard parabola. I'm going to use the fact that I know what this looks like and the points on it to graph this one quickly. So starting with 0, 0, that's like our center point, our vertex. If I flip 0, if I flip over 0, it's still at 0. But then I have to go up 8 units and left 3 units. So let me put some tick marks in here. 1, 2, 3, 4, 5, 6, 7, 8. Let me just label that. And then let's put some here. 1, 2, 3. So the point that would be the center point, or the vertex, would be at 0, 0. If I flip it over the x-axis, it's still there because it's on the x-axis. And then I would take that point, I would shift it up 8 and left 3, and then I would plot it. Okay. And I'll use a table so you can see that I'm actually finding the correct points. I'll show you a table in a minute. So the next point that I know from my original graph, I would pick like maybe 1, 1. And so if I usually have a point at 1, 1, well, let's take that point and do these 3 transformations to it. So first, this one I actually have to flip. So this point is going to flip over the x-axis or reflect. So it was up here, it flipped down here. And now from here I have to shift up 8 and then left 3. So I'm going to go from the flipped version, so reflected down here, I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8, and left 3. 1, 2, 3. Okay. There's our new one, our new point. Let's go ahead and do this a couple more times. On our original parent function, we had this point that we knew, 2, 4. So this point was at 2, 4. So if I find that point on this coordinate system, 2, 4, the first thing I have to do is I have to flip it over the x-axis. So I have to reflect it down here. And so instead of it being at 4 up here, it would flip down to -4. And from there, I would apply the next 2 transformations. I'm going to shift up 8. So from way down here, I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to go left 3. 1, 2, 3. Okay. And that's our next point. So let's just do this one more time. We'll get one more point. Let's pick, let's go ahead and pick this one here. from our original parent function, we know that -2 gives us 4. It's this point. So from -2, 4, that's right here. I'm going to apply my 3 transformations. I'm going to flip it vertically, so it's going to go down to -4. Then I'm going to go up 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm actually back up at 4. And then left 3. 1, 2, 3. Okay. And then you can kind of see the shape already. If I use my last point that I hadn't picked, -1, 1, we would flip it and shift up and left, and that would end up right there. And so there is our parabola. Okay. So that's it with the transformation. We have our original function. We took that graph. You can kind of see it if I just use my paper. That same function, we flipped it over, and then we moved it up and left, and then just plotted it right there. Okay, and that is our transformed function. So what I mentioned was you can still do this with the table, so I'll just show you really quick. If you want to see it, I'll just pick a point or two. So from our table, we can just plug in numbers. So let's say, let's pick -3, because I think maybe you would recognize that one. So if you recognize that -3 was a good number for the middle of your table, because it makes this inside part 0, if you pick -3, we could just plug it right into our function. The function says that you should put negative. Your x value is going to be -3 plus 3 squared plus 8. Okay. And then we just would simplify. So we would say negative on the outside, -3 plus 3 is 0. So 0 squared plus 8. So that's 8. And then I would plot -3, 8. So I would go over 1, 2 to -3. And I would go up to 8. And notice we found that point the other way by just transforming it. So you can always use a table. Like if you're ever confused and whenever in doubt, you can always use a table. But transforming is usually really fast. If you know the parent function, the shape of that graph, you can kind of do it almost by looking some of the time. I went through it kind of slow. I was trying to make sure I gave you all the points, but sometimes you can just sort of recognize that if these are your 3 transformations, your graph flips, goes up 8 and left 3, and then you can like plot your graph like that. And so just finishing this up, domain, of course, is all real numbers, -infinity to infinity. And then this time the range is very different because of the transformations. Your graph goes all the way down to -infinity. So your lowest y value is -infinity. And then this graph goes from -infinity and goes all the way up to the highest point, which is at 8. And you have a point there, so you equal it. Okay, so this is transformations of our quadratic function.